Let's do Calc 2 review, part 4. I've got 67 questions on this review, and I'm way up to problem 21. Aren't you thrilled? Okay, this problem asks to integrate 64 minus x squared over x to the fourth dx. Now, you could try to find some kind of substitution work or integral table that might help with this, but I'm going to do it with trigonometry. Because it's got the difference of squares, I instantly think it's related to trig. 64 is the one that has things subtracted from it, so that must be related to the hypotenuse squared. So there's 8. And then I'm going to put x right there just because it's on the x-axis. So what is the square root of 64 minus x squared? Well, it is over here. 64 minus x squared. So there is a relationship. It's not completed here, but we'll get the rest. So if I do this, let me use an x in the denominator, so this over this gives me tangent. So I've got tangent of theta. So that's taking care of this and one factor of this. Now I need x cubed, okay? If I take this and if I put x cubed in the denominator, I've got 8 over x is the secant of theta. So I need it cubed to get the other 3 factors. So cubing it, it's going to give me secant cubed of theta. Now I need to divide because I don't need that 8. So I need to divide by 8 cubed. Now I need dx. So the simplest x I've got is right here. So x over 8 is cosine. So cosine of theta equals x over 8. So 8 cosine theta is equal to x minus 8 sine theta d theta equals dx. So stick that in. So minus 8 sine theta d theta. So now it's all in thetas instead of x's. I'm going to go into sines and cosines and see if I can't simplify. So let me get rid of one factor of 8. So I've got 1 over 64, and I've actually got a minus there. This is an integral of what? Sine over cosine. So it's right there. Then this is 1 over cosine cubed. And this is sine. And then d theta. So we're right there. This is minus 1 over 64. We've got what? Sine squared. And we've got cosine to the fourth. Now those don't relate too well, but I could kind of split them up and take cosine squared 2 different times. So I'm going to have sine squared over cosine squared, which is tangent squared. And then I'm going to have 1 over cosine squared, which is secant squared. Okay, so which one has its derivative in the problem? It's just simple substitution. Well, the derivative of tangent is secant squared. So I'm going to let u equal tangent theta, du equals secant squared theta, d theta. So I've got u squared here. I've got minus 1 over 64 times the integral of u squared times secant squared theta d theta. That is du. So now we've got minus 1 over 64. Integrate that. U to the third over 3 plus c. What's u? U is tangent. So we've got minus tangent cubed. So minus tangent cubed of theta. 3 times 64 is 192 plus c. Now put it back in x's. What is tangent? Well, it's this over this. So this is minus the value 64 minus x squared to the third over x to the third times 192 actually, then plus c. So not a tough problem if you see the trig that's involved. Now, there are a number of just kind of generic looking integrals that follow this. I'm going to skip some of them and then kind of pick up on some others. So let's go to 23. This one goes from -1 to +1. It's 2 over 1 plus 4t squared dt. Now I'm choosing to do this one because of the definite integral that's involved, and I also want to take a look at the trig substitution because there's also a trig sub there. So let's see what's going on. This thing is a sum of squares, so I'm going to set this up. Okay, so we're adding things, so one of these has to be 1 and one has to be 2t. Now it doesn't matter if I put 2t here and 1 here, that's no big deal. And so this is the square root of 1 plus 4t squared, and so there we go. Okay, so if we take 1 over that, that is the cosine, and it's actually going to be squared, so this is a cosine squared of theta based on this. We've got a 2 with it. Now what's dt? Well, I'm going to take the simplest look of t. So I know that the tangent of theta is 2t. So if I take the derivative, let me divide by 2 just to get t by itself. So here I get dt. Derivative of tangent is secant squared d theta. Okay, so dt equals 1/2 secant squared of theta d theta. So I've got to take this 1/2 secant squared of theta d theta. Well, cosine squared and secant squared cancel. 2 and 2 cancel. So we are going to integrate 1. Okay, so we get theta. Now that's not too exciting, but anyway, we've got to put it back in t's to figure this out. Okay, so let me do the simplest thing. Let me do this. So I know that the tangent of theta is equal to 2t. So what's theta? Well, theta is the arctangent, okay, of 2t. So theta equals the arctan of 2t. And so now I'm here and I've got to go between -1 and +1. So the arctan of 2 times 1, that's the arctan of 2, minus the arctan of -1 times 2. Now I remember from trig that tangent is an odd function, so this minus sign can be kind of factored out here because of the odd scenario. So minus minus gives us plus, so what we end up with is 2 arctan of 2. So there's the answer to that one. Kind of interesting. Okay, let's do a partial fraction decomposition. So this one's number 25. It's got x plus 4 over x plus 1 squared. Now that's a duplicate denominator, so what we do is we say, okay, this one's a over x plus 1 plus b over x plus 1 squared. And we try to break it up that way. All right, so multiply through by x plus 1 squared. What we get is x plus 4 from this. This side, multiplying by x plus 1 squared cancels one of these, but we're left with 1. So x plus 1, and then we get plus b. So one of the easiest ways to deal with this is to let x equal a particular value. So I want to let x equal -1. Now that's not really an option here, but it would work decently here. So if x is -1, we get 3 on the left, get 0 here, and we get b. So b equals 3. Now we need to let x equal something else, and there aren't any more really easy ones to do, but let x equal 0. 0 plus 4 is 4, is equal to a times 0 plus 1, so that's 1a, plus b. Well, we know that b is 3, so a plus 3 equals 4, so a equals 1. So our decomposition looks like this. It looks like 1 over x plus 1 plus 3 over x plus 1 squared. So that's a partial fraction decomposition. Let's go on to another one and just try to work a few different types of integrals and some other types of problems here. So I'll try to stick with integration on this particular piece. Here's an improper integral, jumping to number 29. It is 0 to 9 dx over the square root of 9 minus x. Now that does not appear to be improper because it's not going to infinity, but when x is 9, then this is 0. So it is improper. So what we've got to do is label this some variable like b, usually an early variable in the alphabet. So let's integrate this as x goes from 0 to b. Now, the integral is not that rough, I guess, because it goes from 0 to b. We've got 9 minus x to the -1/2 dx. Do some substitution, and so you could let u equal 9 minus x. du is equal to minus dx, so just a negative in there. And so here's what we end up with. We've got u to the -1/2, so our integral is u to the -1/2. And then we got a minus, and then du, okay? And I'll put the numbers back and use 0 and b, so I end up with minus u to the +1/2, reverse power rule, times 2, okay? So that gives us -2, and u is 9 minus x, so in a radical. So there's the generic answer. Now we've got -2 times the square root of 9 minus x from 0 to b. So put b in there. We've got -2 times the square root of 9 minus b minus -2 times the square root of 9. All right, so this part's easy. This part, not so much, because what we've got to do is we've got to find the limit, because it was improper, as b approaches 9, of -2 times the square root of 9 minus b, and then this one is +2 times 3, so +6. Here you can put 9 in there, so 9 minus 9 is 0. We actually get an answer, okay? So normal limit stuff, you just throw it in and see if it works. It does. So the answer is 0 plus 6 is 6. So this is a convergent improper integral, and not all of them are. Okay, let's try to do this one. This one's number 32. It is the integral from -infinity to e. And the question is 13e to the minus x. 13e to the minus x dx. So if I let minus x be u, u equals minus x, du equals minus dx. So I've got to negate my result here, and I'm going to take the limits off because I changed my variable. So I'm going to have minus the integral of 13 e to the u du. So the integral of that is minus 13 e to the u is itself, okay, which is minus 13 e to the minus x. Put that back in, and now we've got our numbers, okay? Well, I need to put a variable there instead of minus infinity, and then I need to put e here. So now I've got to find the limit as a approaches infinity, negative infinity, makes a difference, of this. Put e in first, so I've got minus 13 e to the minus e minus 13 e to the minus a. All right, we have minus infinity to stick in here, okay? So this is just a constant. It's not a nice one, but it's a constant. We've got plus. Here we're going to have e to the minus infinity. So essentially we're going to take e and raise it to the infinity. What happens to e? E is about 2.71. You raise it to the infinity power, and this goes off forever and ever. So this one is divergent. So it's an improper integral, and it does not have a finite answer. All right, let's keep going a little bit. Let's talk about some series questions. This one is number 33, as long as we're talking about convergent and divergent. This is a series n equals 1 to infinity. And it's got 1 over n to the p. So it says it converges if p is greater than 1, and it diverges if p is less than or equal to 1. Now, that was one statement, and it says, is that true or false? So does it converge for p greater than 1 and diverge for p less than or equal to 1? Well, that's actually stating a p series. And so this one is true. Okay, so the next one, that was A. I should have written it as A. Then, so A is true. Let's check B. B has this. It's got n equals 2 to infinity, 1 over n, ln n, and it's raised to the p. This one says it converges if p is greater than 1. Okay? So what about that one? Well, it is somewhat related to this. Is it the same? Well, not exactly. So you'd have to use some kind of a comparison test to see if that one actually works. Okay? So let's hang on to that one for a while. Now, the third one says this: the integral test does not apply to divergent sequences. Is that true or false? Well, the integral test doesn't apply to sequences at all. It applies to series, not sequences. So yeah, that's true. Okay, so that one's relatively reasonable. The next one says if f of n and a n satisfy the requirements of the integral test, and let's see here, an integral, so 1 to infinity, an integral of f of x dx converges, then what? Then the series n equals 1 to infinity is equal to the integral 1 to infinity of f of x dx. Now that is totally false. Oh, I didn't even have it up here. I'm sorry, you can't even see that. There it is. So if the series information, and I didn't even write that, an, can be worked on with the integral test, and you get a convergent integral, then the only thing you know is that the series converges. It is not equal to this. So this one is definitely false. So what happened was we went to this one. We did not answer that one as true. It looked kind of like it might be, well, it said which one of these 4 is false. That one is the one that's false. So there we go. Okay. We've got some different tests and try to figure out if some of these converge or diverge. And so let me try one of those. Let's look at this one. It's listed as number 37. Number 37. It asks for the root test. So here's our series. We've got n equals 1 to infinity. And we've got 1 over n to the 8th minus 1 over n to the 10th. And it's all raised to the nth power. Now we're supposed to use the root test. The root test. So the root test is this. It says to find the limit as n approaches infinity of the nth root of this. 1 over n to the 8th minus 1 over n to the 10th raised to the nth. Okay, and then see if that is in fact less than 1. There's the root test. Well, this part's pretty easy. So let's figure out the rest of this. Well, how do we subtract these two and what do we do with them? Okay, so these are not series at this point. What we're doing is we're testing the values. So I want to get n to the 10th as the denominator. So that's going to make this n squared over n to the 10th. So the limit as n goes to infinity of, now we've taken the root off, so we've done that. So we've got n squared over n to the 10th minus 1 over n to the 10th. Okay, so what's that as n goes to infinity? Well, you know, it is the limit as n goes to infinity of n squared minus 1 over n to the 10th. Now what is that? Well, it is an indeterminate form because as n grows without bounds, so does this, and so does this. So we've got an infinity over infinity. Let's use L'Hopital's rule. We're going to do that. We can. So take the derivative of the numerator. So the limit as n goes to infinity of, let's see, we've got 2n, and here we've got 10n to the 9th. Well, we can reduce a little bit. This becomes a 5. This becomes an 8. So now we've got the limit as n goes to infinity of what? Well, it is of 1 over 5n to the 8th. Okay, that goes to 0. So if we've got that going to 0, then what do we have with this? Well, we end up having something that is in fact less than 1, and so it converges. Okay.